All right, we'll get started. My name is Gabriel Gonzalez. I am a software engineer at Twitter, and today I'm going to be talking about secure execution of untrusted scripts. So before I begin, I want to ask the audience one question. Oops, one second. Who has ever done something like this, where some installer asks you to install their software by doing curl, some URL which contains the installation script, and pipe that into bash, sometimes with root privileges? Who's ever done that? Yeah, a lot of people. I've done it myself, so you're just as guilty as I am. And what I would like to do, actually, is to fix this problem, to provide a secure way to install scripts such that they execute with a very restricted set of privileges. However, this talk is actually there's an entire website which is dedicated to gross violations of this principle. It's called curlpipesh.tumblr.com, and you can see lots of egregious examples of this, even from very large popular software packages like NPM, Rust, Nix, and lots of other things. However, the talk of the title might be slightly misleading. Usually I tend to work more on what I call foundational libraries. And so this is actually just one practical application of a foundational library that I'm working on. And so this talk is going to explain what that foundational library is and how you can use it to build secure installers and possibly other applications as well. So in the first part of the script, I'm going to give a motivation for why I want to be able to create secure software. And the second part of the talk, I'm going to give an end-to-end walkthrough of how we actually establish security across the pipeline. And the way I'm going to divide this up is it's actually in terms of three modular software pieces. One's going to be a core calculus, which I've built, and that has a front end and a back end, which are used as part of the compiler pipeline. And finally, at the end of the talk, I'll give a conclusion, and if time permits, we can actually do a live demo where somebody from the audience actually gives me some code, which I will run from my laptop, and I won't even check what the code is. So the actual foundational library that I'm trying to build at the moment is what I like to call the Internet of Code. And the reason I call it the Internet of Code is the Internet because it's distributed, and you actually use the Internet as the distribution mechanism, meaning that every type, term, value, or function in this language has its own URL. So you can host all of these on their own network endpoints. For example, if you have your laptop with you right now, you can curl that URL right there, sigil.place/talk, it's this talk, number 0, that I've given on this subject. And then there's a true value that's hosted on the network. And that represents how true is encoded in this core calculus that I'm building. In this case, it's a lambda calculus. That's why you see lambdas in that code. I don't expect you to understand lambda calculus for the purpose of this talk. Just know that it's sort of a low-level encoding for functional languages. And what's neat is that expressions can have references to other expressions. So you can, for example, here is an expression. This is the implementation of the OR operator in this language. And it has references to remote URLs. So you can see this hashtag introduces a remote reference. And in this case, it's a reference to a type. So I'm saying here, you can roughly read this as saying, the value B1 that I'm binding has a type which is given at this URL, the URL for bool. And you can also provide URLs for terms, like true there at the bottom. And so by doing this, expressions can transitively refer to other remote expressions, which can in turn refer to other expressions. The only restriction is that A, it has to be well-typed, B, it can't be recursive, and C, it has to form a directed acyclic graph. And the compiler will enforce all of these properties at compile time. And the existing software architecture that this most closely resembles would probably be JavaScript, although the comparison is not exact. So in JavaScript, you can obviously host code at arbitrary endpoints, and you can include that. If it's within the same domain, you don't violate cross-domain security policies. And so in theory, you could do that. But there are some important differences between this and, let's say, JavaScript. First one is that this has a much lower barrier to distribution. Hosting code is just as simple as posting text to a URL, and embedding it is as simple as a hashtag URL reference. There's no ceremony involved in distributing code. But another really important difference is that it is typed. And the reason this is important is that I want to use the type system to enforce policy. Because if I'm going to be injecting remote expressions directly into my syntax tree, I want to have some say over what those expressions can be. Did anyone attend Justin's talk earlier on Haskell and PureScript? If you attended that talk, he explained that one of the benefits of a type system is that a type not only says what something can do, but more importantly, what it cannot do. So for example, we can use a type like bool to enforce something like that, saying this can either be only a true or only a false. It cannot be a side effect. It can't be a function. It can't be like some remote code injection that does anything other than being true or false. And so types can be a way of enforcing policy. And I'm going to show a concrete example of how we can do that for a real-world program with side effects. So let me give you an example of how this would work at the very low level. So let's say I have 3 network endpoints hosting code. So the first one here at the top is going to be hosting the OR function. And then we also have a network endpoint for true and network endpoint for false. And since these are valid expressions within this language, I can apply a remote URL to another remote URL. So here I can take the compiler for this core calculus, which is called Morte. And Morte will take an expression on standard input. So here I'm just typing this in, let's say pasting this in at the command line. And then it will output an expression on standard output, which has been type checked, has all remote references resolved, and then fully optimized. And so here I'm saying I'm going to apply the OR URL in prefix form to 2 arguments, the true URL and the false URL. And so Morte will recursively resolve all these expressions and remove all remote references. It'll type check the program to make sure that it's valid. And then it will optimize the program at compile time. So we haven't actually done any code generation yet. So this is all compile time evaluation. And Morte will output 2 lines. One is the inferred type of the program. So Morte says the type of this result is going to be a bool. Oops. And then the value, and it optimizes away or true and false to true at compile time. Like Morte is really good at evaluating things. I'll give a few more examples of that. But as you can imagine, it would be really tedious if we had to provide fully qualified absolute references to URLs everywhere throughout our program. I don't even want to do that myself. But what you can do to make programming in this style easier is that you can actually create local aliases. Because this hashtag syntax works for things other than URLs. You can also import local files using either relative paths or absolute paths. So for example, if I want to create a shorter reference to the bool URL, I can just create a file, a local relative file named bool, whose contents are just hashtag the remote URL pointing to bool. And now I can use this within my program just by saying hashtag bool, and it will import the file named bool, embed that into the syntax tree, and that will in turn contain reference to the remote URL for bool. Then it'll embed the contents of that into the syntax tree, then type check things and normalize things. So if I want to create convenient ergonomic shorthand aliases, I'll just create shorthands for bool, true, false, and an OR. And now I can run the same program as before, but now all I have to do is just say hashtag OR, hashtag true, hashtag false, and again, it will resolve everything and give me true evaluated at compile time. Morte, though, is just one piece in a more modular and reusable software architecture that I'm building. So Morte is a very bare bones language. It's highly minimal. I'll show you what it looks like in later slides. It only has 3 purposes. One is that it links code, which is what I used to refer to resolving remote expressions. It type checks that code to enforce policy, and it optimizes that code at compile time as much as possible. And it's a total language, meaning that it can actually do a lot of optimization at compile time because it can make assumptions that other languages cannot make. But programming in Morte is actually really difficult to do. Like, I wouldn't want to do it myself. So I've created a front-end language, which I like to call Anna, which is just a higher level language that is more convenient to program in, that compiles down to this low-level core calculus called Morte. And Morte itself, though, is not an executable program. Again, it's just text, like those example files that you saw before. So we need some way to take those Lambda expressions and turn them into real executable machine code. And that's the responsibility of this Nordum component right here. And Nordum is also what's responsible for enforcing policy, making sure that only things that we whitelist will survive the transition to generating machine code. All of these projects have two APIs, so they're all Haskell libraries, so you have a Haskell API for generating or compiling code, but they also provide a command line interface as well. So if you don't want to ever have to depend on Haskell, each of these provides an executable, which takes something on some text on standard input and pipes something on standard output. And the current progress of these projects is that Morte is essentially done. It's ready for public consumption, well documented, stable, and Anna, though, is almost done, meaning that the compiler is done, but it also comes associated with a library of standard utilities I'm going to be building. In fact, you can actually see those standard utilities online. There are URLs, like the ones we've been looking at. So here, for example, is a server that I'm hosting, which is just a file server. And so all these are just files. For example, here is going to be the implementation of the side effects type I'm going to be using later in this talk. You have files which correspond to the original Anna source code, and then side by side with the Morte encoded value. So for example, here's the encoding of the IO type, the side effect type in Anna, and then when I pass it through Morte, I get something that looks like this low-level lambda calculus right here. So these are all ready for distribution within any Morte code. The Morte compiler, on the other hand, is highly experimental. It's just a really hacky backend that I pieced together just for this talk. It's not ready for public consumption at all, but it works, even if it's incredibly dirty. So eventually I'll polish this and release this as its own separate library. But right now, you'll just have to trust me for the more Morte examples. And the talk will show how we can actually chain together these three components in order to be able to securely run all of these remote expressions that we sprinkled all over the internet. So the challenge is that I want to safely import and execute arbitrary code, and I want to do it over an untrusted network, so no encryption, no authentication, no code signing. I don't even care if the code itself was written by the NSA trying to infiltrate my system. Okay, I'm assuming the program is a complete enemy, and I don't even need to necessarily trust the programmer at all. And so the way I'm going to do this is I'm going to split a program essentially into two phases. In one phase is where we do things that are entirely pure, harmless. So that's type checking, optimization, and linking remote expressions. The worst that can possibly do is it just wastes my CPU, maybe takes up a little bit too much memory, downloads too much code from the internet. We can solve that using quotas, but it can't really destroy our system. And then there's a second part, which occurs in the machine generation step, the code gen step, where we actually compile the program to a real program with side effects. And the boundary between the pure phase and the side effect phase is enforced using just one type, enumerating what are the side effects that we're going to whitelist. So in this code architecture, all pure computations are automatically whitelisted. You don't have to explicitly ask permission from any central authority to distribute them. But the set of side effects that we're going to allow our secure installer to support must be explicitly whitelisted by the backend as the only things that it can support. And we can customize the backend to allow different sets of side effects for different application domains. All right, so I'm going to give you an end-to-end example of a real side effect program being compiled to machine code. Do you have any questions before I go on to that section of the talk? Okay, good. So the running example is we want to distribute safe installation scripts. And I just picked 5 side effects that might be useful for installers. This is definitely not a comprehensive list. This is just purely for the purpose of this talk. And our installer will only be allowed to do one of 5 things. It can either read a string from standard input, it can write out a string to standard output, it can download a file from some URL to a local file path, it can create a file from a string, and it can test for a file's existence. Notice that it's not going to be able to do things like remove files. Okay, so the worst thing that the installer can do is perhaps do a denial of service on my hard drive by filling up a partition. Okay, that's probably the worst case scenario for these 5 effects. So obviously, there's always potential for insecurity in the set of side effects that you choose. Like maybe creating a file from a string is not necessarily a secure enough side effect. Maybe I want to do something like create only X bytes worth of data as a side effect, which would be more secure. But these are simple enough for the purposes of this talk. And so these all have associated types. So for example, this is a type which says this getLine command is a subroutine, which I'll denote by IO. So IO stands for a subroutine that returns some value. In this case, the value it's returning is going to be a string, the string it read from standard input. And then there's going to be a putLine command, which takes some argument named str, that's a string. And then it will give me a subroutine that will print that string and return a useless value. So I use prod0, sorry for the name, to represent that useless value. That's sort of analogous to void in the C or Java family of languages. or unit in Scala or Haskell or PureScript or other ML-like languages. And then you have download, which you give it a URL and you give it a destination to copy the URL to, and then that will give you a subroutine that actually executes that copy. And then, of course, create file, you give it a payload, a path, the contents of the file, the path you want to write out the file to, and that's a side effect that has no return value. And finally, test file. You give it a path to check for the existence of a file, and then it will have a subroutine that will return true if the file exists, or false if the file doesn't. Here's an example script, and this is written in the ANA language. There's some little boilerplate at the top. You can tell I like Haskell because I called this a monad. Sorry about the name. I know some people don't like the word monad, but I am unapologetic about it. And so this is the part of the script that you should actually care about, which are these 5 statements that we're going to execute. And so here we're going to say the first statement is just going to print a line to standard out, prompting the user to enter a file name. This has the useless return value. It's an empty return value. So I'm just going to use underscore to indicate that I'm discarding the value. And then the user is going to enter a line of input. So I'm going to get a line from the user using getLine, and I'm going to store that result in this dest variable right here, which has type string. And then again, I'm going to prompt the user for the file contents, read that in as the payload variable. And now that I have both, I can just create the file for the user. So I'll take the payload the user gave me, the path that they gave me, and then create a file with that contents at that location. And so what I can then do is I can take this and pass it through an end-to-end interpreter. So this would be the secure client that I would distribute that takes scripts and then executes them in a secure way. And so I'm not going to really care where these hashtag references came from. So they currently refer to local files on my system, but those files might refer to remote expressions. I don't really care where they came from. And it's going to parse this code, compile it down to the core calculus, resolve imports, type check, normalize, generate machine code, and then it's going to actually run the program. And then it's going to prompt me to enter a file name. Let me actually show this in action, because I have this working here on my laptop, but let me make that bigger. There we go. All right, so here is the actual program in question. It's a real program. And then I have an interpreter function, which will basically take that program and will do everything I just showed you. If I modify the program, it'll update to reflect the updated program. Give it a second. Type checking and resolution takes the most time because it's getting things over the network. Here we go. So it prompts me for a file name. I type in output.txt, and then the file contents are going to be hello world. That's totally obligatory for any introductory tutorial. And now if I look at the contents of output.txt, there it is. It's hello world. So the program is successfully compiled, and it can only run with the side effects that I specified. If I try to put in any other command other than the 5 side effects that I told you, this program will fail to compile completely. So the entire pipeline begins with this ANA program, so I use the .ANA suffix to indicate ANA program. And what we're going to do is, the first step is to translate this higher level ANA language into the low level calculus of the Morte language, which is the calculus of constructions. And so I can do that just by piping it through the ANA command. So ANA just desugars from the higher level language to the lower level language. So in goes this, and out comes this right here. All right, so notice that this is very low level. Everything is done entirely in lambda calculus. All these C's and S's you see right there, that's the lambda calculus encoding of an ASCII string, actually. And then here's the entire program, and here you can see some of the utilities at the bottom. But notice there's some things we haven't done. So this still hasn't resolved all remote imports. We haven't really type checked it, and we haven't optimized or normalized the expression. So the way we do that is piping it through Morte. So Morte takes a Morte program on standard input and type checks it, resolves imports, normalizes it, and outputs the optimized version on standard output. So I'll just pipe that through the Morte program. Then I'll get something that looks a little bit bigger, like this. So now all remote references have been resolved. It's been fully inlined and normalized, giving me this program right here. And now this is ready for code generation. So I'm going to pipe this through the Nordum executable, and that will enforce policy. It'll verify that this program only restricts itself to the 5 side effects that I set out at the very beginning, and then it will generate executable code. And actually, because this is a very hacky example that I put together for the purpose of this talk, it's actually going to go through in Haskell intermediate. Haskell is the back-end language. And so what it'll actually do is it'll take this, and it'll generate the equivalent Haskell program. So it just took that lambda expression, translated it to a shorter Haskell lambda expression without explicit types. And then there's this adapter function, which it inserts for all programs, which basically translates all these lambda calculus encoded types to the equivalent Haskell built-in types, so that it can actually generate machine code. And now this program can be piped to run Haskell to generate a real executable that does exactly what the first example did. In practice, the code that I ran just did all entirely within one program instead of the command line, but it's functionally equivalent. So I'm going to go into more details now about how the core calculus works and how it supports this sort of type checking, normalization, and resolution. Any questions before I go on to that stage of the talk? Excellent. So Morte is a really, really low-level functional language. And by low level, I mean that the only things that are in Morte's syntax tree is you have the type of types, which we'll denote by star. All right, you have bound variables. You have lambdas, which you can think of as anonymous functions. So if you're programming a functional language, you might be familiar with lambdas. It's just like this is saying an anonymous function which takes an argument x of type A and then returns a b. And then we have pi, which is sort of like a function type. So this basically says this is a function that takes a value named x of type A and then returns a value of type B. Then you have function application, which basically that's represented by app. So app fa just means apply the expression f to the expression a as a function. And then finally we have remote imports, which are this import constructor right here. And there's nothing else. There's no side effects, no strings, no numbers, no anything. It's just pure lambda calculus. And then the only important operations which Morte exposes are load, which is how you resolve all remote expressions. And so that replaces all these import constructors with remote expression syntax trees. We have the type checker, which given a fully resolved expression will tell you either the expression does not type check or it will give you its type. And finally, we have normalize, which will take an expression and just keep beta reducing and eta reducing the expression to give you an optimized program. Here's an example program, Morte pipeline. So again, we start with our original or true false expression, and the first thing Morte will do is it will take each one of these three hashtags and replace it with the equivalent remote expression. So or will be replaced with this lambda expression right here. True will be replaced with this lambda expression right here. False will be replaced with this expression right here. And then it's going to optimize the program just by constantly beta reducing in this case. So it's going to do beta reduce, beta reduce, beta reduce, and that gives you the fully optimized at compile time expression which evaluated down to true. So Morte is sort of like a functional assembly language, but it differs from a lot of languages that are functional in that it's total, meaning that you don't have general recursion, and also it means that every expression has a normal form, which is fully optimized. It means that compilation and type checking, it means that evaluation is always guaranteed to complete within a finite amount of time. Total you can think of as being a non-Turing complete language. Pretty much every other language you're used to is Turing complete. But a language does not necessarily have to be Turing complete to be useful. Morte is 100% pure, meaning that it has no built-in side effects. In fact, the way we're going to represent side effects in Morte is just we're going to build a pure syntax tree describing planned side effects. So Morte evaluating things doesn't actually trigger any side effects. Instead, we're just going to pass that pure tree to the backend, and then the backend understands that tree and then translates that to all the side effects that it will explicitly support. Another really important thing, in fact, this is actually very hard to find in any language, which is why I had to write my own, is that Morte has no escape hatches or unsafe primitives whatsoever. Everything you saw in that syntax tree, that's it. There's no unsafe perform IO, there's no primitive FFI operations that break referential transparency. There's literally no way to break out of Morte security guarantees other than a bug in the compiler. And so like I mentioned before, no support for strings, numbers, data types, or pattern matching. You can't even have multiple top-level expressions. All Morte programs are just one big, giant expression. You can't even have a recursion. But it turns out that you actually can translate all those features into Morte anyway. And there's several papers that actually explain how to do that, which are fantastic. And so Anna's job is actually to take those higher-level concepts and then translate them down to this core calculus. So any questions before I go on to how Anna works and it does this translation? Okay. So if you want to have multiple top-level expressions, you can use let. So we're going to create a new top-level binding called x, which has type t, and it equals y. And that can be translated to an anonymous function, which basically says we're going to bind a value name type x, which is going to come here from y, and then that will give us back an e. You can have multiple lets just by nesting multiple lambdas, and it's the exact same way. You can define functions. So I can say define a function which takes two arguments, x1 of type t1, x2 of type t2, and it returns y, which has type t. And that scopes over this expression e. And that, again, can be completely converted to lambda calculus. Now, where it gets really interesting is how you convert data types to lambda calculus. So that's actually possible, and it's rather actually difficult to understand at first, but it works really, really well. So if you are familiar with Haskell or any similar language, you can declare data types like in Haskell like this. You say bool. The type bool is either a true constructor or a false constructor. And the equivalent type declaration in ANA says, here you have a type bool. It has two data constructors, true and false. We can also explicitly name our pattern matching function. This will be if in this case. And this type definition will scope over this expression e. So it's not a global definition. And that can be desugared to lambda calculus. You don't need to understand that desugaring process other than it actually works. And there's a great paper explaining how it works, which is called Automatic Synthesis of Type data structures in the lambda calculus, also known in shorthand as Bohm-Berardici encoding after the authors of the paper. And what's cool then is that once we have this construct right here, we can separately compile all those expressions. So I can actually separately compile bool, true, and false, so I can host them all on their own network endpoints. So for example, if I want to separately compile bool, I'll just give the type definition and say, given that bool is true or false, give me the definition for bool. And then that will output this right here, which I can then save on the network. And I can do the same thing for true, false, or if. And they'll all work together in exactly the right way. And they will have no references to each other. So these four separately compiled expressions will actually be totally self-contained. You can encode records in the exact same way. So here's an example of a pair of record with two fields in it. So it says this type pair has one constructor called makePair, and a fields named x and y, and a pattern matching function called foldPair. And then that will, of course, generate the equivalent lambda calculus expressions, which I can now host on the network. And so we can do string literals can be encoded in lambda calculus. So in ANA, when you type in a string literal, it will actually translate that to a giant lambda expression. And here at the beginning, this was hello world. And then you can see this is basically an ASCII encoded hello world, HELLO, comma, space, WRORLD, exclamation mark, end of string, right here. And once you have an encoding for strings, you can encode things like string concatenation. You can encode all string operations using pure lambda calculus. So here, if I can say in ANA, concatenate the strings hello and world, pipe that through ANA, pipe it through Morte, and it will concatenate them at compile time. So here again is hello world encoded in ASCII lambda calculus. You can encode numeric literals in lambda calculus. There's a simple and obvious way, which is the way usually taught in the literature, and actually uses a more efficient representation using binary numerals. So 42 gets encoded as 1 in binary 1, 0, 1, 0, 1, 0, which is binary for 42. And you can do 64-bit arithmetic totally in lambda calculus, and it actually completes within a somewhat reasonable amount of time, a second. This is done at compile time, so you only do it once. And so here's an example of adding two 63-bit numbers to get a 64-bit number. Here is multiplying two 32-bit numbers to give a 64-bit number, all done at compile time. And then once we've translated things to lambda calculus, now we can start generating machine code. And the machine code generator is actually pretty efficient, even though it's using these large lambda expressions, because Haskell compiler is really good at optimizing them away. Any questions before I go on to the back-end code generation? So, like I mentioned before, Morte has no built-in side effects. Instead, we're going to encode a side effect as another data type in the language. So here, example is how we encode the data type for side effects, which is IO. And the way I'm going to represent it is as a syntax tree, which has 5 nodes and an end of tree. So each one of these constructors right here is one node in a syntax tree, which behaves like a placeholder for the equivalent side effect on the back end. For example, this putLine constructor right here is a placeholder for the real putLine command. And it takes a string, which will eventually be passed to that command, and then this will be the remaining statements to execute. Similarly, getLine is a placeholder for the real getLine command, and here's a function that will basically consume the string read from the real getLine command. And so once we have the syntax tree defined in Anna, we can then ask Anna what is the equivalent Morte type for that tree. And we'll output a type that looks like this. It's basically a function that takes one argument for a constructor, and this is essentially a signature for all the side effects that our system is willing to support. So we can actually read from the type that this will only support putLine, getLine, download, create file, and test file, and nothing else. And so now that we've encoded in the type system, we can actually use that type to enforce policy. So we can take any program that is generated by the Morte compiler and just type check it and see, does it match that type, yes or no? If the answer is yes, we do code gen. If the answer is no, we abort compilation. And we'll get a type error explaining why it didn't match that signature. And so this policy enforcement is done at compile time. So like if you're thinking about what security systems this is most similar to, this would be closest to the sandbox approach to security, where you're essentially whitelisting interactions with the outside world. But the difference here is that we're enforcing that whitelist at compile time instead of runtime. So before we even do code generation, we can detect if our program is enforcing, it matches our policy or not. We don't have to like throw in an error for partially abort a script that happened to do something it wasn't supposed to do. So like I mentioned before, since we can specify the side effects in the language, that means we can customize what side effects we can specify. That means if you want to have a different set of whitelisted side effects for a different application other than secure script installation, you can do that just by building your own IO type and generating the equivalent Morte type, and then type checking that before doing code gen. And then you have to write the backend to do the translation of those constructors to the equivalent real commands in the backend. So this approach is most similar to the sandbox approach to security. The most unique feature is that it detects policy violations at compile time. But other important features is that pure code is automatically whitelisted. So in a lot of other security managers, you either have to do a blacklist approach if you don't want to just like automatically reject all code, or a whitelist approach, which requires tediously like whitelisting the entire standard library of the language and requiring library authors to do some registration policy for whitelisting their code. But by dividing code into pure and side effect phases, we can just simplify things by only requiring you to explicitly whitelist side effects. And this allows us to automatically accept pure code. Another important advantage over other security systems is the extremely low barrier to code distribution. If you think about it, the typical way you will distribute code in another language is that you first author your code, and then you'll create a package for your code, and then you have to author some like package description, all right, and then you have to upload that code to some package repository. Then a user has to download that package from the repository, add it as a dependency to some build file in whatever build tool that they're using, and then they have to import that package using some import statement, and then they can use your expression. But here, all we have to do is just host it on a network endpoint, and then somebody references it with hashtag URL, and you're done. That's the entire distribution process. And the other thing that distinguishes this from other security approaches is that policy is enforced using types, which means that the more advanced the type system gets, the more types of things we can enforce at compile time, which is really nice. All right, do you have any questions so far? So I'm going to give a few concluding remarks, and if time permits, which I think it does, I'm going to actually try and do a live demo with a member of the audience, where they will just like put up some code on the internet, and I'm going to use it inside my script. It'll be pretty simple code, but just to drive the point home. So one thing I would recommend is I would say like these projects are not really ready for general purpose use. Like I would not recommend that you use them right now. I don't think they're ready for that. Things that I need to do is that it would be nice to allow the users to select more high efficiency numeric string operations that get done at runtime instead of compile time. That would be a nice feature to have, especially when doing like numerical code. Type inference is still missing. So the Anna language is still an explicitly typed language, which can make it tedious to use for highly generic, highly polymorphic functions. So in the absence of type inference, I wouldn't recommend it for general purpose use. And then finally, it needs really better tooling for things like how to distribute code, like how to take a bunch of things that are on your files, a library of code, and host it in an easy fashion. There needs to be some way to easily discover all these remote expressions sprinkled all around the internet. And there needs to be an easy way to install code. And where here installation just means creating a file, a local file that aliases some remote file. That's all installation really is, just creating shorthand aliases. There needs to be an easy way to do that en masse for installing a package. And this code is real. It's up on GitHub. So the Morte library can be located on GitHub, Haskell Morte library. Same thing for Anna. The Northern code right now exists purely on a branch of the Anna library. It doesn't have its own repository just yet, but you can actually check it. It's there. And if you have any questions, of course, you can reach out to me. My Twitter handle is GabrielG439. I also like to hang out on R Haskell as the TechMo user. And unless you guys have any questions, I want to actually do a really quick live demo. So first off, I want to mention that a lot of these expressions are hosted online. So here's the actual, I mentioned the place right here. And what I want users to do, actually, in this case, is I'm going to write 2 programs, and one of you in the audience will actually select which one to run. So here, I'm going to actually open up an example. So we already had one example program right here, so the example.anna code. All right, so I'm going to move that to, let's call it io1.anna. All right, oops. So first off, in order to import that, I need to translate it to a Morte expression. So I'll say Anna, import io1.anna, and move that, and just make that the IO file. And it's going to take a while to do the sugaring because it's actually type checking the result, and type checking IOs with strings in it takes a while. So this is why this process is actually taking a few seconds. Give that some time. There we go. So here is the expression in the core calculus. All right, and then I need to create some other file. So let's call this io2.anna. And so this file is just going to say, because I don't want to take too many risks while doing a live demo, I'll base it off of my other file. So here I'll just do a simple echo program that will take some string read in from me. Sorry. And then it will print that string. Okay. There we go. All right. So let's type check that, make sure there are no bugs in it, and then output that to io2. Give it just a second. All right, so now let's create a final program, so now a new example.anna. And so what I'm going to do is I'm going to import some user code, so this is going to be a URL, and I'm going to apply it to either io1 or io2, and the user gets to select which one to run. Is there anybody who wants to volunteer to host text on a remote endpoint? Does anyone have internet access? Justin, you want to be the volunteer? Okay. I think we can do this really easily using lpaste. Okay. Let's see if there's a way to get raw text or something, so I'm going to try it myself. So here would be like the polymorphic identity function in Morte. So I'm going to just see if I can get, okay, public. See raw. Yeah, that'll work. I think perfect. Let me see if that generates something valid. Excellent. That'll work. All right. So now using lpaste, I'll give you a rough template for what this program should look like. So one thing that will just help really quickly is to get the URL for I/O. Okay. So if you can actually navigate to, so this URL right here, can you navigate to that and just copy that? So that's just the path to the I/O type. Sigil.talk place/talk/0/IO. And then you can write an expression that looks something like this. So you'll say, I'm going to take 2 I/O actions, so let's say call it io1, and you're going to give the type that we pasted up here. So, sorry, this I/O, oopsies. So this I/O type, make sure there's a space, no ending slash and a space after it. Okay. And then another I/O type, io2, hashtag the URL, no slash or space. And then I'll let you select which one to run, using either io1 or io2. and I'm going to use your code within my program. All right? Tell me whenever you think you're ready. Okay. And so now, paste that, and do you have the URL? So do a public paste, or so just do something like this, public, let's say. All right. And can you give me the number for that lpaste that you hosted the code for? Okay, so you were right after me. Perfect. Oh, sorry, I shouldn't have looked at the code because I don't want to like see what you're actually running. Again, the idea is that I shouldn't care what code you put in there. All right, so now I'm going to go to example.ana. Oh, sorry, I already had it open. And I'm just going to use your URL. Boom. Okay, and you're going to pick which one to run. All right, and now interpret. Status code exception, it was an invalid URL, not the correct text type. Oh, damn. Okay. Well, anyway, let me then just take your expression and then just make a local file out of it for the hell of it, just to demonstrate the rough concept. Okay, so where was it? Where was I before? Here we go. Okay, so I'll create Justin. There we go. Okay, and now vi interpret, sorry, example. So I'll just refer to the Justin file exited. All right, and now let's do interpret. Oh, sorry, what is? No, actually, oh, maybe there is. No, it doesn't look like there is. Hold on one second. Let me actually read it. Oh, okay, I see. Because there actually is a problem in the remote string type that I hosted. It's not encoded correctly. Okay, so then let me actually modify your example a little bit further. How embarrassing. So I'll just let you use the one I have locally instead. Okay, and then let's try it. There we go. Oh, sorry, that's just the, here we go. Actually says there's a type error. Oh, so it caught a problem at compile time. Invalid input type. Oh, that's right. Now I see what the error is. So there was a type error in both of our programs. It actually should have been this. We have to specify what the return value is of these actions. So it detected a problem at compile time. Now it's succeeding, hopefully, and then give it just a second. So again, resolution takes a while. It's getting things from the network, type checking these large syntax, lambda expression syntax trees. There we go, succeeds, generating an executable, and he selected the first program, okay? And so that's the end of that example. All right, sorry about the problem with the string encoding. Apparently the code I hosted was not encoded incorrectly for Morte to download it, but yeah. All right, so are there any questions? If not, then that's the end of the talk.